The next property of systems is the stability. So if you remember, when we talked about the invertibility of the system, you talked about one example where we try to integrate. If you feed in a constant signal as the input to an integrator, we started seeing the output to be infinite. The constant signal is a very practical signal. For example, you just turn on a circuit with a battery connected to it. The voltage is going to be a constant, let's say a 3-volt battery or 1.5-volt battery. It's a constant signal that is fed to it. Right? So if that is the kind of input that you're going to feed in practical setups, and then the output turns out to be always infinity, if you let's say put in an integrator and observe the output, then it turns out the output is unstable, right? This is not really very useful system many times, because we are getting an unstable output. We are feeding in a bounded input and then the output goes unbounded. Such a system is called an unstable system. So in practice, many times we want only a stable system. And how do we characterize a stable system? We say that a stable system has this BIBO property, which means bounded input produces bounded output. Bounded input, bounded output is what we call as BIBO. Right? Bounded input produces bounded output. Such a system is called a stable system. You don't expect a system to produce unbounded output, right? So let's say you are trying to hear to music, and then you feed in a nice music signal to your headphones, and then the headphones is producing all like maximum volume, just a constant signal. Then it's going unstable basically. So it is just shouting at its maximum volume, just like a screeching noise. That is not what you want. You want it to be a stable system. When you feed in a stable input, you expect the output also to be stable and bounded. If that is not happening, then that is not a useful system. So what we want in practice many times is to ensure that our systems are stable. And for that, we need to make sure that this property is satisfied. So whenever you feed in an input which is not going to infinity, the output should also not go to infinity. That's all we are looking for. Very sensible expectation. And many times we will use this condition to check if the systems in real life that we are designing are unstable or not. So it is really, really important many times to ensure that the system is actually working in practice. Very often, this will be a very useful property to check. So when you start constructing electric circuits to, let's say, design filters, remember the very first problem that we encountered was trying to filter out different frequencies in audio signals. So we don't want one filter to always give, plus VCC, where VCC is the battery voltage. It should not work like that, right? You feed in some signal as the input, and it should not keep shouting all the time at maximum volume. So we want it to be stable. Okay, some examples of stable systems. So what if you have a system y of t which is producing x square of t? This is always a stable system, because if I feed in an input which is bounded above, the maximum voltage level is, let's say, some V, then the output also is bounded above. The maximum voltage of the output is V square, not more than that, right? So this says that the system is going to always be bounded above, meaning it is always going to be finite, and this property is satisfied. Hence, this is a stable system. But if you remember our discussion of invertibility, this system was actually not invertible, because the input could be -1, the output will be +1, the input will be +1, the output is still +1. So for two different inputs, we get the same output. So this is not an invertible system, but it's still a stable system. Often people think that invertible systems are stable systems, but that is not true. So for that, we have another example here. So if you see this setup, there exists an inverse for this system. What is the inverse? So you can always find the x of t as y of t by t square plus 1. This is never going to be 0. Okay. So the inverse will always exist, right? The inverse will always exist, but this is unstable. Why is this unstable? Let's say that x of t is going to be taking only finite values. So it is always important to note that when you are checking the stability, You have to first ensure the input is stable. What we mean by input is stable is the input never takes a value which is infinite. So if you're feeding an infinite input, then you should not expect the output to be finite. So that is not what we are looking for. We are looking for a BIBO stability, meaning you're saying input is first of all stable, then you're expecting the output to be stable. So let's say we are always feeding an bounded input here. What can happen to this output? The output can grow unbounded because of this t square plus 1. So let's say now x of t is a constant, it's a bounded input, right? Now what will be the output? T square plus 1 plus c. If you plot this, how does it look like? Now it will look like something like this. It's a parabola basically, where this is c, which means as t tends to infinity, y of t also tends to infinity. It grows unboundedly. You cannot bound and say that y of t value is going to be below this. It can keep growing forever as t tends to infinity. So y of t tends to infinity in this case, which makes this system unstable. So now there can exist systems which are invertible and still be unstable. There can exist systems which are non-invertible and still be stable. So essentially what we are saying is stability does not in any way affect invertibility and the other way around. These two are independent properties. Okay. Let's see some examples. Alright, now let's take the same cases that we were discussing earlier. If the output is to be given by the input plus some constant, is this a stable system? Yes. This c is a fixed constant. So if x of t is less than infinity, then x of t plus c is also less than infinity. Hence, this is stable. Now, what about this setup? Now, here we are going to assume that small a and capital A both are less than infinity. So, if x of t is less than infinity, then obviously x of a t plus b is also less than infinity, because this is only a delayed or advanced and a shrunk or a compressed signal or a stretched signal, which means the signal itself cannot grow in amplitude. And we are saying that the multiplication factor is finite, which means this is also stable because y of t cannot grow to infinity as long as x of t is less than infinity. What about this case? Now this is the case that we just saw. Here, let's say x of t is a constant for x of t is equal to, let's say, 2, just a constant. Then what happens to y of t? Y of t is 2t square plus c. So as t tends to infinity, here y of t tends to infinity, which means this signal is growing infinitely with time, and hence the system as such is an unstable system. Okay, now what about this system? If we had y of t to be equal to cos x of t, then that is a stable system. This is stable because cos can never give you a value which is more than plus 1 or minus 1. So this is always a stable system. But if we had tan, then we know that tan 90 degrees is actually infinity. So obviously we now know a scenario where the input is bounded but the output is growing to infinity. Hence this is unstable. Okay, now what about this? Taking the derivative. Again, just to look at it, it appears as if it is a stable system. So you give an input which is bounded, you take the derivative, it appears as if it will be a stable system. But think of an example where x of t is equal to u of t. What is this? The corresponding output is d by dt, which is the Dirac delta function, if you remember. The Dirac delta function, even though if it has an area 1, its instantaneous value is infinity. which means instantaneously at time t is equal to 0, this grows to infinity even though the input was a bounded input. Hence, this is an unstable system. So the most famous differentiator and integrator are neither invertible nor stable, and hence the study of signals and systems becomes even more important, because the most practical examples that we are going to talk about are in non-invertible and non-stable or unstable systems. So we need to carefully design setups in our circuits so that we don't end up with unstable systems. So we need to really analyze things properly before we can design circuits, because a simple integrator and a simple differentiator are unstable. Okay, what about this system where you simply take a product of the signal with its delayed version? If x of t is bounded above, x of t plus t is also bounded above, and hence their product is also bounded above. So if x of t will take a maximum value of 10, x of t plus capital T will also take a maximum value of 10, and the product can also take a maximum value of only 100, not more than that. Hence, this is a stable system.